Perfect. So I think I might have the longest name of my presentation for this conference. It's called Millions of Transactions per Second on a Single Machine, Case for Virtualized Database and Scaling. And my name is Roger Johansson, and I'm a Senior Solution Architect at StarCounter, and you can find more information about StarCounter at starcounter.io. I'm also the founder and creator of two quite big actor model and distributed frameworks for .NET, Go, and Java space. The first one is Aka.NET, which is a port of the famous JVM Aka. And the second one is a spin-off from that called Proto-Actor, which is, I believe, the first cross-platform actor model framework where you can have actors written in C#, Go, and Java communicating in the same database clusters. You can find me at Twitter at Roger Alsing, and the same for GitHub. And you can also find these slides for this presentation under github.com/rogeralsing/presentations, and there's a StarCounter presentation there. I usually deal with actor model, scalability, and distributed systems, and C#, Go, and Kotlin. But today I'm going to talk about the StarCounter platform and what we are trying to do at this company. So, to set the agenda for this talk, first I'm going to try to explain what we are trying to achieve at StarCounter, talk about our application platform and micro applications, and then we're going to dive into what we are doing with in-memory computing and the StarCounter information operating system. We are going to look at the future of hardware, and we are going to look at the Mars project, which is a code name for the next version of the StarCounter database. So, we have what we call an application platform, and what that means is that we have a stack which looks something like this, where developers could choose some form of front-end framework like React or Polymer. Then we have our own bits in this stack. The first one is Palindrome, which is a framework for communication over REST and WebSockets. And what Palindrome does is that it applies JSON patch protocol, so you can have patches of model changes streaming from the client side to the server and from the server back to the client side. We also have the application block, where you define your own view models, your own database entities, and your own application logic. So basically, this is where you write your own code. And then we have the StarCounter in-memory app platform. This is where we have data mapping, we have persistence, we have queries using SQL, etc. So that is the actual foundation that the platform runs on. If we compare this to the traditional stack, if you were to write a really snappy client-side web application today using traditional tools, you would probably have some form of front-end framework, maybe React, Angular, Polymer. But you would also have quite a bit of client-side code defining your application. If you look at YouTube or Gmail, etc., then there's a fairly large chunk of JavaScript code powering those applications. Then there will be some form of network boundary where the client-side application communicates with some form of services or WebSockets and contracts, etc. You have your application code, and maybe you have some form of object relational mapper or something similar for other databases. And then you have yet another network hop to your database. And that's pretty much how traditional web applications are built today. What we are doing at StarCounter is what we are calling collapsing the stack. So instead of having all of these bits and pieces that we have in the traditional stack, you still have the front-end framework. You could use React or Polymer, like I said before. Basically, any templating engine that can take a client-side model and render that as HTML. Then we have this network boundaries still, because the server is, of course, on the back end. But the communication between the front end and the back end is done with this palindrome framework. So we define our view models, pretty much just saying that this view should have these following properties, and this should be mapped from the server to the client and back again. Then you define your application, and your application consists of your business logic, your entities, and validation logic, etc. And then we have the Star Counter in-memory app platform, which runs on the same machine but in a different process. So we don't do yet another network hop. We actually communicate over shared memory between the application and the platform. So by doing this, we have a lot less code because we remove some of the parts of the layered cake. But also we increase the speed and lower the latency of the application, since we don't need to jump across networks in the same way, and we also have this really effective patch protocol that can send data back and forth between the client and the backend. So you gain both the maintainability and the performance by doing this. And this brings us to a concept which we call micro-applications, and this really builds on top of the traditional idea of microservices, but we want to take it yet one step further. So if we look at how you build applications, in this case we would have, for example, 3 applications. We have application A, B, and C. And if we don't have anything more, those applications would be completely separate and independent. But what we do in the Star Counter platform is that we bring something which we call client-side blending. So you could say that my application should consist of these 3 other applications, and I want to compose them on the client side in this following way. I want to have application A as this big chunk on the left side of the screen, and I want to have application C as this main content area, and maybe application B as some form of top navigation bar. So that way you could take pre-existing apps built on the Star Counter platform, and this is the main idea of the platform itself, that anyone can build completely independent applications, and then you can glue them together with minimal effort to build something bigger from that. So if we look at this screen, this is from our internal intranet, and I have to apologize for the bad resolution because I have zoomed out this screen just to show all of the different elements on the screen at the same time. So this is one of the screens covering people in our intranet, and the person up here is Stefan, my boss. And if we look at how this page is composed, we can see that all of these different colored blocks here are different applications built in Star Counter. So at the top we have this profile application, which really just displays profile information. And embedded inside this profile application we have the image application, which really can show any image, but in this case this image application is embedded in the profile application, and thereby it can show images of the person that the profile application is showing. Then we have an organizational application showing what department this person belongs to. We have some form of user application describing your username and the rights you have on the intranet. At the bottom we have some form of quick note system where you can write notes that are stuck to this profile. And at the right we have this timeline, and now this timeline happens to be empty, but you can think of that as some form of social wall like Facebook or LinkedIn, where you see different events popping up there. So how we compose these different applications, in this case each of these applications would have their own data model. So the profile application would have maybe a profile entity with a first name and a last name, and the user application down here would maybe have a user entity with maybe also first and last name. And what we do inside the Star Counter database, we can map these properties to point to the same space in memory. since we are an in-memory database, we can do projections on top of the underlying data. So we do this by what we call mapping, and I cannot go very deep into details about the mapping layer because there's some patent pending about that, but we can cover the idea of it. So if someone were to update data in the user entity, those changes would be caught in the model for the user, and then that would trigger a mapping effect down in the mapping layer saying that, yeah, this entity has now changed, so let's also update the information in this profile entity. So that way we can keep objects in sync. Right now we are using materialized views, so we are keeping double copies of the data, but we are completely ACID and we use snapshot isolation, so there is no risk of having data going out of sync. There is no eventual consistency going on between the applications. We are currently working on having a shared, more fine-grained data model beneath this, so you don't have to store the data in duplicate formats. And this also enables us to do what we call data flow programming, or maybe you're more familiar with the idea of Excel-style programming. So inside Excel, you can do things like you can have different fields where you write data, and then you could have calculated fields where you calculate some total. For example, you could have price and quantity, and you could calculate the total from that. And I can show a quick demo of how we can do this in the star counter world. So I hope everyone can see the screen right now. So in this case, we have defined a view model where we say that we have price and we have quantity and we have total. And inside the code behind for this model, we can say that I want the total to be the price times quantity. And I want to bind this model to this HTML template. So this is pretty much my entire application. I have this template saying that this is how I want to render this model onto the browser. And this describes the format of the data. And the actual application just says that anytime you hit the base endpoint for this application, return this page. So if we look at this, how it would look like. So there's nothing fancy going on here. Let's say I write 4 and 10 here. We can see that the total is being updated in real time as I write here. And this is actually done using this palindrome framework. So anytime I write on the client side here, it will update the client side model, calculate a diff patch to see that what has changed in this model, send it to the server. The server has a copy of this model since we are an in-memory database. You can have all the validations and business logic on the server. If anything needs to be updated back on the client, the server can send a patch diffgram back to the client. So that way you can really build real-time and snappy applications that react on changes on data. You don't need to set up your own WebSockets. You don't need to do all the boilerplate things that you usually need to do when you're dealing with complex front-end systems. So, going into the in-memory aspect of this presentation. In-memory for real. If we look at how applications has been built in the past, you would probably have some application process where you have an entity, in this case some form of person object. We have Alan Turing, who died at the age of 41. And we have a database process containing a table of people. If we look at the old disk-based databases and disk-based systems, the main source of truth was this disk where the data was stored. So those databases were optimized for spinning disks and moving arms. And there's a lot of overhead to that, like we heard on the keynote this morning. Then you have this network hop or some form of inter-process communication. Then you probably have this object relational mapper to map the relational model back to, for example, an object-oriented model. And all of this introduces quite a bit of overhead in latency and friction when building these applications. Later, we also got in-memory databases, but the concept has still been pretty much the same. You have a separate database process, maybe on a separate machine, but now the source of truth is the memory part of it. Some of them have support for stored procedures, where you can run the stored procedures in memory, but as soon as you're going to deal with this data inside your application, you still need to cross these network boundaries and still need to transform this data using some form of mapper into your host process, be it Java or .NET or whatever. In our case, what we are trying to do, or are doing, is that we remove all of that, and then we just replace all of the communication with shared memory. So we have the database process running on the same machine as your actual application. And the database process holds all of your data in its own special database in memory. And instead of holding a copy of your entity data up in the application process, we now only hold an object ID in this object. So whenever you try to touch a property on this person object or whatever it might be, then it will actually pull the state from the database process and read that from there instead. So we remove a lot of the overhead of crossing network boundaries, and we remove all of the complexities of mapping back and forth between the object relational model and the object-oriented model. So we have the same model on both the application process and the actual database process. That means that we can also do things like this. Let's say that we have some application running in C# and some other application running in Node.js, and if they both operate on the same objects, they could still have these proxy objects which points into this shared memory and operate on the same data. So instead of having one copy in your database, another copy of the data inside your .NET process, and yet another copy of the data inside the Node.js process, we only hold one copy of the data, period. And that's how we do it. How we make this work is, for example, let's take an example in C# code. This is how you would define your entities. You would just write a normal POCO class, in this case person, and this person class has a first name with a getter and a setter. In C# we have the concept of auto properties, which has these get and set properties. So if anyone is from Java space or anything, you would probably have a get and a set method instead. And when you compile this code using the C# compiler, you would end up with something like this. So this class would have this private string first name, which is really the state container for the first name, and then the property would just read or write to this state container. But that is not what we want to do in our case. We want to have this state inside the database level instead of holding the state inside the object here. So what we do is that we have what we call a post-compile weaver, which continues where the .NET compiler ends. So this is output of the .NET compiler, and this is the output of the star counter weaver. So we remove this state container field inside the person entity and replace this with just an object ID. And then we rewrite the code inside the properties. So the properties now instead get and set the data from the shared memory in the database process. So this get and set part of the code now interacts with the database process using shared memory. And this enables us to do millions of operations per second, really. So if we take this classic example. Maybe we have a customer. The customer has many orders. Each order has many order details, and each order details might have one product associated with that. So doing that in the traditional world with, for example, an object relational mapper, there's really only two ways to deal with this. Either you could use lazy loading or you could use eager loading. And in the case of lazy loading, if you first fetch the customer and then navigate the orders property of the customer, that would trigger yet another SQL statement to the database. And if you then start looping over all of the orders, then if you access the order details of a specific order, that would trigger yet another SQL statement for all of the order details. So that is what's called ripple loading in the object relational world. So if you try to build this report system where you just want to do reporting over this object model, that could end up with hundreds or maybe even thousands of SQL queries. And I don't really know how many systems I have been debugging during my days as a consultant where people have used something like Entity Framework or Hibernate in Java, who have really done exactly that, because when you work with an object relational mapper, it looks like you're working with normal objects. It looks like you're only traversing stuff that are in memory, but there are side effects which cause things to be loaded from the database. So if all of that data needs to be fetched one by one from the database, that is going to introduce a large overhead in terms of latency and throughput. The other way you can do it with most object relational mappers is using what's called eager load. And when you do eager loading, you need to say up front that, yeah, I want to load this customer, but I only want to load the name and address maybe. And then I want to load all of the orders and maybe just the top 10 order details per order. And I also want to load the product name. So in those cases, you need to clearly define up front exactly what you want to touch, which can be sort of complex to define that. The object relational mapper also needs to be able to translate that specification into a query that can run in a single statement at the database level, which most object relational mappers are pretty bad at doing. If you look at how Hibernate or Entity Framework does this, you will end up with these cross-join queries which are really super inefficient, and there's a lot of data being pulled up. And another issue with this model is that once you start passing these objects around, if you have some code taking an order, for example, that code cannot really reason about what parts of the order has been loaded, because you can't really see that. It looks like it got past a complete order, but maybe only the order date and shipping number and the order details were loaded. But you can't really see that on the object, so it gets hard to reason about those kind of object models. So what we do instead in our model is that since everything is in memory, all of the data that has been committed is already available to traverse. So when we are traversing these kind of object models, we don't need to do this kind of exponential queries where we do more and more queries. We just chase pointers in memory. So you say that, yeah, I want to load this customer. And once you have that customer, you also have the pointers to all of the orders. So you can just traverse those, which then in turn has all the pointers to all the order details. So you can really traverse this as if it was a normal object graph residing directly in memory. But in this case, with the benefit of actually having indices and all of the optimizations that a database can provide for you. So this makes it a lot faster to build that kind of applications, because you both get the speed from it. You don't need to think about optimizations in the same way. You can just code as if it was a real normal object model. So in this case, we see a user interface from one of our customers. They are called modular management. They build a system called Palma. And they build this configuration tool where they can configure different products. So we see this grid-like thing with rows on the left side and columns on the top side and different symbols inside the grid zones. So what they do here is they have this super complex model where the model is actually versioned. So first of all, you can scroll back and forth in time. You can say that I want to look at how this product looked 10 days ago. So everything is versioned, everything is kept in place, and you can do this in real time. So all of this triggers hundreds and hundreds of queries on the same page, but since we already have all the data in memory and we can utilize all the indices, this can be completely real time. So it's really interesting to see how complex systems our customers are building with this technology, because things like that would be really hard to build with classical tools, because you would have to pre-calculate all of this so you have all of the data denormalized. But then again, if you want to keep all of the state and history available at the same speed, then you would have to have denormalized copies of the entire history of all the products, which would consume a lot of disk space and memory. So, just to try to prove that we're not completely lying about the 1 million transactions per second, I have this example code, and this is of course super naive example. It just sets up an endpoint. It loops from 1 to 1 million, and then it triggers a individual transaction for each of those iterations. And then at the end it will wait for all of the transactions to complete, and then it will output the time. And please notice that I'm running this on my laptop, and my laptop is probably not completely okay with the power here in the States either, so and of course we need to have a little bit of demo mess up here. It doesn't seem to start at all. So let's see if I happen to have this. Yeah, let's stop that one. They happen to start on the same endpoint. This in the previous application. Maybe we need to start it again. It doesn't matter really how many times you try this before the presentation, but so let's see if we can stop that too. Now we have no applications running, and let's see if we. Okay, maybe we shouldn't spend more time on this thing. For some reason, my computer seems to freeze when I try to compile this. It's not even starting to compile. Okay, let's skip that one and see if we can run it at the end of the presentation instead. But running this example code on my machine usually takes between 1 and 2 seconds to run 1 million transactions. And that is not 1 million individual objects only, it's 1 million objects each in their own individual transaction, where we also guarantee that we persist it to disk. So it's not only pushed into memory, it's actually also flushed to the to the log on disk. So you get ACID transactions, we have snapshot isolation and guaranteed disk persistency. And of course, on a bigger machine than this one, and given that the actual code starts to run, we can easily do more than 1 million transactions per second, which is completely impossible to do on a normal machine using, for example, SQL Server. So is there any way that we could go even faster? Why do we cap at about 1 to 2 seconds on my laptop here? And that is because we are capped by disk I/O, because we guarantee that when you commit your transactions, we actually flush that to disk also. And we cannot go faster than you can write to disk. Of course, we could say that I don't want to wait for this transaction to be flushed, but then you don't have any guarantees that the data is actually persistent. So currently, the disk I/O is the bottleneck in our case. And that brings us to the Mars project, the next generation of the Star Counter platform. So we have the future of hardware. If we just look at the cost of 1 megabyte in US dollars from 1980 to today, the cost has gone from like $300 something down to almost nothing. And we believe that this is a trend that will continue, that memory will be cheaper and cheaper and cheaper. And due to this trend, of course, we will see bigger and bigger machines with more and more memory. There is also another trend going on that different vendors are trying to solve the problem with persistence. So instead of just having, like we have currently, where you have magnetic disks or solid state, and then in the in-memory part of systems you have registers, you have your different caches, and then you have your main memory. For example, Intel is right now working on building these non-volatile memory RAM chips, where you could have RAM that is actually non-volatile. So that changes the game for us, because that is a lot faster than actually writing to a solid state disk. So these non-volatile memory chips are maybe 2 or 3 times slower than normal memory, but still a lot faster than writing to disk. So we are hoping that this will enable us to go maybe 10 times faster than we do today. And that would really be a game changer for building systems on this kind of in-memory technologies. And these chips are coming out, I believe, late next year. I believe we have people from Intel here that could answer when that is about to be marketed. So, Star Counter on the CPUs of 2018, and this is a Mars project that we are working on right now. The new design is that we will have this Delta store where all the writes goes into, so when you update or do any transactions, that will be written to the Delta store. And the Delta store is kept in memory in normal volatile DRAM. Then we also have this main storage, which resides in this non-volatile memory, in the non-volatile memory chips, not non-volatile disks, but actually non-volatile RAM. So the Delta store will be merged by batch updates from the main memory into this non-volatile memory. And that means that when you read data, we can read it both from the Delta store and from the main storage. And this changes the game quite a bit for us, because currently, when we restart our databases, we have this database log where all the transactions are stored. And currently, when you load from disk and restart the database, we need to load the entire transaction log, replay that in memory, rebuild all of the indices, and that can take quite a while if you have a really large database. But having this non-volatile RAM chips, we could store all of that completely in RAM. So when you restart your database, it's just there. You don't have to wait for anything. So we believe this will be the complete game changer for technologies like our own. And this brings us to the future of software architecture, because currently the trend is that we're going towards smaller and smaller machines. We have Docker containers, people are building microservices, and that is introducing a lot of network overhead and a lot of complexity to manage all of that. But if we now have really large machines with terabytes of memory, and if this memory now is persistent, then why should we scale out to all of these small machines? So our prediction is that instead of seeing all of these small machines with different microservices running individually on them, we believe that you will see fewer but bigger machines where the applications actually run in memory and communicate with the in-memory technologies on those machines. And that is all that I have on this topic. So, any questions on? No?
Is your current technology software alone, or is it hardware?
It's software alone. So it can already be downloaded from starcounter.io. So it's a standalone database and application process that is currently it's only for .NET. The database is actually written in C and C++, but the actual application hosts are .NET only. But with this Mars project, we are changing that to also include Node.js and Python, and in the future probably Java also.
Is this open source or closed?
It's closed source. There are some talks about open sourcing some of the parts. For example, this Palindrome framework for doing the client-to-server communication, that is open source. That can be downloaded from the Palindrome organization on GitHub, for example. But the database technology itself, it's closed source right now. Yeah, so with that, I would like to thank everyone for coming here. Yeah, one question more.
Can you talk a little bit more about the shared memory process?
So what we do is we set up this memory chunk where we hold all of the both the ongoing transactions and the committed data in a somewhat compressed format. We don't compress primitives like integers or numbers, but we do compress strings. So we use a format called turbotext to compress strings. So strings will not occupy as much memory as it would do if it were UTF-8 or UTF-16. So we do some compression on that level, but when you have these objects running in .NET space, for example, and you try to access some property of that, it will call into this database shared memory and pull that memory up and decrypt or decompress those strings. So there is a little bit of overhead compared to having the objects completely in .NET space, but by far less than having it in a separate database.
So are you making any attempt to do horizontal scaling with this?
Yes, that is also coming in this Mars project. So we will do data partitioning on that model. Currently, the current version of StarCounter is single server, where we are also looking at having failover to a hot standby. But the next version of StarCounter will be horizontally scaled.
Only on a partitioning scheme?
Yeah. Yeah, so thank you for me.